So this video, we're going to discuss the idea of convergence of sequences. So first of all, the first question is just when does a sequence converge? So I'm assuming you know what a sequence is, but when does it converge? So we say that a sequence a sub n converges to the number L if for every positive number epsilon, there corresponds an integer n such that the absolute value of a sub n minus L is less than epsilon when n is greater than big N. Little n is greater than big N. Okay, so this is a pretty heavy definition, and if you've been in calculus for a while, this is very similar to any other epsilon delta definition that comes up with a lot of different topics in calculus, so it shouldn't be surprising that such a definition exists even for sequences. And so we'll kind of play around with this in a second, but we will say that if no such number L exists, then we do say that the sequence converges. So either a sequence will converge to a number L or it diverges. Those are kind of the two options there. And just as a notation note, so if that sequence converges to L, we can write either the limit as n approaches infinity of a sub n equals L, or we can just write a sub n with an arrow to L. So we call L the limit of the sequence. So limits and sequences really go hand in hand. But the thing to keep in mind, right, is that a sequence is a list of numbers. And so we won't have a going to infinity. It's this idea of n going to infinity. It is this idea then, right, that at some point you get to enough terms where all of the terms converge to a certain number. So at some point in that list, they converge to a certain number. And you can really see that also in this definition, in the way that this is stated. So there comes a point where there is some number where when we kind of get above that, we like see really clearly that our sequence converges to that. That's literally baked into this by saying that this when little n is greater than big N. It's kind of referring to that idea there. Okay. So maybe just to play around with this definition a little bit, let's talk about proving the limit as n goes to infinity of 1 over n equals 0. So again, remember, this is referring to a sequence, right? So it's not enough just to say, oh, n is going to infinity, so I know what this is. We do actually have to use that longer definition of the limit. And so I'm thinking of something that works like this. But for now, what I'm going to do is I'm going to use that epsilon definition of the limit. So I need to refer to exactly what was in that definition, right? So we talked about that we need this, so the sequence minus L is less than epsilon when n is greater than, little n is greater some larger number. So the whole goal here is to figure out what is that number that we have to get larger than. So like I said, we're going to start by, here's my sequence minus the limit. This is going to be less than epsilon. So really all we need to do at this point now is, so notice that this is now in terms of n. So if I'm trying to figure out what is that number that little n needs to get over, I really just need to solve this for n. And so this is not too hard to solve for because this just becomes, of course, the absolute value of 1 over n is less than epsilon. And if I want, I can just flip this entire inequality. So this is a property of inequalities that I can take the reciprocal of everything. If I take the reciprocal of both sides, I just have to flip the direction of the inequality. Some people forget that this is a thing with inequalities, but it is a thing. So I can use this, and now I can actually point out right away what that number is that little n has to be bigger than. So as long as little n gets greater than 1 over epsilon, we have fulfilled this definition. And again, I know it's always like a dense thing to look at, so I like to point it out over and over again. But this is really the heat of what this, or the heart of what this is trying to get at, is if you can determine what is that number that little n has to get over, then you have fulfilled the definition. And so we have done that, so we are good to go. So I can say then when big N is greater than or equal to 1 over epsilon, then the limit holds. Another limit that we can talk about is the limit as n goes to infinity of c equal to c. So this would be a constant sequence of just the same number over and over. And for this one, so if I set this up, so my sequence was c, but my limit was also c. So c minus c is going to be less than epsilon. This equals 0. So since this distance is equal to 0, what this means is that for any positive value of n, this limit will always hold. And that makes sense, right? Because every single term is already equal to the limit. So this one kind of has an intuitive sense of like, okay, for any number, this is always going to be true. Okay, so the real takeaway that I do want you to take from this, though, is that there are two main limits now that we can count on. The limit as n goes to infinity of 1 over n equals 0, and the limit as n goes to infinity of c equals c. So these two we're going to play around with, of course, in a moment as we learn more about limits with sequences. The next thing that feels like the right thing in this progression of talking about convergence of sequences is we should have some rules for limits of sequences. So I'm going to have two sequences, a sub n and b sub n, and we're going to let the limits of those be a and b respectively. Okay, so if this is true, if we have these limits, then we get the following rules. The first one is the sum rule, which says that if I take the limit as n approaches infinity of a sub n plus b sub n, this equals a plus b, so I can just add the two limits together. A similar rule holds with the difference rule, so if I subtract these two sequences, I can just subtract the limits. Next, we have the constant multiple rule, so that's going to be if I have k times b sub n, k can be any number that we want. This is equivalent to just taking k times that limit b. Up next, we have the product rule. So the product rule says the limit as n approaches infinity of a sub n times b sub n, this will equal a times b. And then finally, we have the quotient rule. So if I'm taking a sub n over b sub n, I can just divide the limits. And so that is, those are some of the standard rules that we get. So knowing those rules now, we can apply this to more difficult limits. So what I want to do is I want to determine whether the following converge or diverge. That's all I want to know. So I have this sequence 1 minus 3 over n plus, or sorry, 1 minus 3 over n over 1 plus 3 over n, or 3n. Ugh, can't speak. Okay, so the easiest way to handle this actually is to divide the top and bottoms. Whatever you do the bottom, you have to do the top to keep everything equal. Let's divide everything in here by n. This will be an equivalent sequence, but then we will be able to much more clearly see this. Oops, this is supposed to be a minus, sorry. Okay, so this is what I want to take the limit of then. So if I take the limit as n approaches infinity, so what does this all simplify to? This becomes 1 over n minus 3 over 1 over n plus 3. And now I can really just focus on taking the limit of each part of this. So 1 over n and 1 over n, these are both going to end up going to 0, right? That was one of those key takeaways that we just had. And then for minus 3, this is going to converge still to minus 3, and this one's going to converge to positive 3. So what is actually happening here? We have 0 minus 3 over 0 plus 3. So I have negative 3 over 3, so this will equal negative 1. So that's what this whole thing will end up converging to. So having those limit rules and then those base limits that we kind of started with, there's a few algebraic manipulations that we're allowed to make here to figure out the value of a whole bunch of different limits. Okay, so what about if I have a sub n equals the square root of n? So what about this one? Okay, so with this one, like if you just think about it, first of all, I don't have anything, like my key takeaways, right, were these were the two limits that I know. And then when I think through all the rules that we just talked about, I didn't say anything about square roots. So right away, you should be a little bit suspicious about this. And if we just start thinking about what are the terms in this sequence, so this will be 1 square root of 2, square root of 3, square root of 4 is 2, square root of 5, square root of 6. So what is happening with these terms? These terms are just getting bigger and bigger, right? And so if I get to like the, 7,000th term, right, it's just going to keep growing. This sequence diverges because it just keeps growing and growing. It's not going towards any particular number. It's just going to continue to get bigger. Okay, so moving on. So now I've got 3 plus negative 1 to the n over n. Okay, so for this one, it might not feel like it at first, but you can actually use the same trick that we used in the first one. So what I would encourage you to do is to pause the video here, give this a try, and then hit play when you're ready. Okay, so what I'm going to do is I'm just going to go ahead and set this up, and I'm going to go ahead and divide everything by n, so you can just kind of see what's happening here. So I've got 3 over n plus negative 1 to the n over n, and then n over n is going to equal 1. Okay, so This one I think can be a little bit confusing for people. So let's go piece by piece. So 3 over n as n goes to infinity, this is going to 0. 1 is just going to 1. And then what is happening with this one here? So this one kind of messes with people because I know that it goes from positive to negative. Well, the reality is that it doesn't really matter necessarily. Like there comes a point, right, with this particular one. So once we get out to say like the millionth term, it doesn't necessarily matter if I'm talking about positive 1/1,000,000th or negative 1/1,000,000th. They still are getting pretty close to 0. So this negative 1 to the n is not impacting or like making anything mess up, I guess. So this is also going to 0. So my value here then is 0 plus 0 over 1. So the value of this limit is just actually going to equal 0. Okay, and I have one more here. So once again, I want to encourage you to try this one. So give it a try and then hit play when you're ready. So once again, the first thing I'm going to do is I'm going to divide everything by n, and I'm just going to do it within the square root. So I'm going to have the limit as n approaches infinity. So I'll leave the square root here, but I'll divide everything by n. So 2n divided by n is 2. N divided by n is 1. And then I'm left with 1 over n here. Okay, and so now as I go through and I take the limit of everything, so this limit I know is going to 0, and this part is going to 2, and this part is going to 1. So what do I get? I have the square root of 2 over 1 plus 0. Those are all the pieces. So this is just going to end up being the square root of 2. So this limit does indeed converge. We're good to go. Okay, so now we're going to talk about a few more theories here. So next I want to talk about the sandwich theorem for sequences. So the sandwich theorem for sequences says, if I have 3 sequences, a sub n, b sub n, and c sub n, if these are sequences of real numbers where a sub n is less than or equal to b sub n, which is less than or equal to c sub n, so if this relationship holds at some point, at some certain index, then the limit as n approaches infinity of a sub n equals the limit as n approaches infinity of c sub n equals L. So if these limits out here equal L, then the one in between also equals L. So at this point, you should be familiar with the sandwich theorem from an earlier calculus lecture or class. This is very, very similar for functions as it is for sequences. It's the same idea. And we can really apply that logic to this sequence here. So if I wanted to determine whether this sequence converges or not, okay, well, here's a challenge for you. Can you figure out how to sandwich this particular sequence so that we can use this sandwich theorem? Challenge for you, I would say pause here, set up how you think you might do this, and then hit play when you're ready. So the way that I would do this is, so sine of n, so really any sine or cosine function, it's really the same trick. So the thing that we always know, right, about sine and cosine is that they are between -1 and 1. So we always kind of start a sandwich there. And then obviously I want to have everything over n, so then I can divide each part by n. And so from here, now I can say the limit as n approaches infinity of -1 over n, well, that's going to equal 0, and that is equivalent to the limit as n approaches infinity of 1 over n. So these two n's are both equal to 0, so therefore I can say then that the limit as n approaches infinity of sine of n over n also has to equal 0 by the sandwich theorem. So that's a really classic way to use that. The next theorem that we're going to talk about is the continuous function theorem for sequences. So if a sub n is a sequence of real numbers, or we're going to say let, I said if, we'll change that to let a sub n be a sequence of real numbers. So if a sub n converges to L, and if f is a function that is continuous at L and defined at all a sub n, then f of a sub n is going to converge to f of L. Okay, cool. So this is now opening up a lot more things that we can do with our sequences. So I have this next function here where, and we kind of actually already use this in some sense, but if I have this function here, so what I can do is I can think about just the inside part of the function at first. If I wanted to, I could break it up like this, where I have n plus 1 over n. And of course, with this limit, I could just apply some algebraic rules, so I can break this up into 1 plus 1 over n. And so I can see that this particular limit is going to converge to 1. So if it's easier for me, I can start by working on the inside, and then I could define my function f equal to the square root of a sub n. So then what that means is f of a sub n is going to converge to the square root of 1. So that's just also going to equal 1. So that's what this function is, or that's what this theorem is saying, is that if it's easier for you to work on this and then kind of figure out what happens with the outside part of that function, you can think of this as a sequence within a function, and you will get to the answer that you need. Now, another kind of connection between functions and sequences comes from this other really important theorem. So suppose that f of x is a function defined for all x greater than or equal to n sub naught. This is an n sub 0, so this is called n sub naught, that's what we call it. And a sub n is a sequence of real numbers such that a sub n equals f of n for n greater than or equal to n sub naught. So then the limit as n approaches infinity of a sub n equals L when the limit as n approaches infinity of f of x equals L. Okay, so this is actually a really cool theorem because what it does is it establishes a connection between sequences and functions. And you may have already kind of felt like, oh, it's just a function with a list. When you look at sequences, it is really that in a lot of cases, right? Where we kind of still treat it with like the same as we would with function notation. So this theorem now formalizes that there is such a connection between sequences and functions. And what's the best part about this is if we can now relate limits of sequences to limits of functions, then what that does is that allows us to use L'Hopital's rule with sequences, right? Because typically we use L'Hopital's rule when we're taking limits of functions, but now that I have this connection between the two, now I can use L'Hopital's rule with limits of sequences. So I can now start to do really funky sequences, say like the limit as n approaches infinity of natural log of n over n squared. So we know that this is going to equal 0, but why? Well, you could tell now by looking at this, so what would I get as n goes to infinity? I would get infinity over infinity. And so that is a classic use of then L'Hopital's rule. Now, I will say this, if you are rusty on L'Hopital's rule, I do think that's going to kind of hurt you with sequences. But I do have a video where I review everything. I have a summary of L'Hopital's rule. So I would strongly recommend that you go check that out if you need a refresher, because I'm just going to assume that you know it here, but I will drop a link to it in the description below. Okay, so anyways, so we are talking about this limit as n approaches infinity. So since I have infinity over infinity, what I can do is I can take the derivative of the top and the derivative of the bottom. So this is going to be 1 over n over 2n. Okay, from here, I can rearrange all of this. So this is going to be 1 over 2n squared. And 1 over 2n squared, so now we're good to go. This is just going to end up equaling 0. So that is why the limit ends up equaling 0. Okay, what about if I have the limit as n approaches infinity of 4n plus 1 over 4n minus 1 to the n? So this one's a little bit trickier and is also an application of L'Hopital's rule, but it's an application with one of the exponential indeterminate forms. So let's now just review how do we use L'Hopital's rule in a case like this. So the idea would be that first I take the natural log of this entire function. And I'm going to have to do something to I can't just take a natural log out of nowhere. At some point, I have to resolve the fact that I did take this natural log, but for right now, we're just going to go ahead and take the natural log. Okay. So now that I've taken the natural log, what this is going to allow me to do is I can bring down the n. So this is going to be the limit as n approaches infinity of n times the natural log of 4n plus 1 over 4n minus 1. Okay, now at this point, it might not look like we can use L'Hopital's rule, but what I'm going to do is now I'm going to use a really classic algebraic trick that we do use with L'Hopital's rule, so I'll make a little space. Okay, and so what that algebraic trick is that I'm going to rewrite this as 4n plus 1 over 4n minus 1, all of this over 1 over n. So natural log divided by 1 over n is the same as multiplying by n, but it just allows us now to put this in a fractional form. And what this does is this takes us actually from one indeterminate form to another one. So the other thing that I guess I kind of want you to note with this is, so with this natural log of 4n plus 1 over 4n minus 1, okay, so if I just think about what is actually going on with just this part here, so if I divide all of the inside parts here, so if I divide everything by n, so what would I be left with? So this would be 4 plus 1 over n over 4 minus 1 over n. So as n goes to infinity, this ends up looking like the natural log of 4 over 4, and so that's just going to be the natural log of 1. So that just equals 0. So the reason why this matters, that it matters that you kind of notice all of that, is that, and so actually I should probably put a limit in there just to be proper. Limit as n approaches infinity. Okay, so all right, so the reason why this matters is, so I have n times this thing that is effectively 0. N times 0 is an indeterminate form, but now that I have rewritten in this form, so I know that this part here equals 0, and now the limit of 1 over n as n goes to infinity, this is also 0. So what I mean is, now I've rewritten this in 0 over 0 form, and so this is a really classic L'Hopital's rule trick. Okay, so I'll clear some space, and now we party on. Okay, so since this is now 0 over 0, now I can take the derivative of the top and the bottom. And I would actually recommend that you pause the video here and you try that on your own just to make sure that you get the right derivative, just in case you're a little rusty. All right, so at the top, we've got to roll up our sleeves here and use chain rule. So I've got 1 over 4n plus 1 over 4n minus 1, and then I have to multiply that. So that's the derivative of the outside function. And then we have to multiply that by the derivative of the inside function. So hopefully you remember your quotient rule. So I take the derivative of the top and I leave the bottom function alone, and then I subtract off the derivative of the bottom and I leave the top function alone. And then I have this times 4n minus 1 squared. Whew, a lot of stuff going on here. And then, so this is just the derivative of my top function. So now I also have to take the derivative here. So this is going to be negative n to the negative 2. Okay, so we need a little space now. So let's unroll all the algebra going on here. So first of all, this part here, so I am actually going to rewrite it instead of 1 over this. I just really need the reciprocal. So I don't want to have to write everything down again. So I'm actually just going to kind of cheat this a little bit. So I'm going to rewrite this as 4n minus 1 over 4n plus 1. So I just needed to take the reciprocal. And now by doing that, that actually saves me a little bit of space. So I can see that this will cancel out with this 2. So I can cancel those out. Now we do want to be careful here. You don't want to start canceling out this 4n plus 1 with anything up here until you've simplified everything on top, because I have this minus sign in the middle, so I do have to finish all these operations. So let's see. So I've got the limit as n approaches infinity. So let's see. This is going to be 16n minus 4 minus 16n minus 4. And then all of that times 4n plus 1. So that was that one, and then 4n minus 1. So I multiplied this with this, and I still have this negative n minus 2 in the bottom. Okay, so yeah, so now I've got all of that good to go, so I need some more space. And I can see here that my 16n's dropped out. So it looks like I'm left with negative 8 over 4n plus 1, 4n minus 1, all of this divided by negative n to the negative second. Okay, and so now, let's see. So now I want to simplify this. So this is all going to be, so let's rewrite this one more time. So this is divided by negative n to the negative second, but what does that even mean? This is divided by really 1 over n to the second. And so if I'm dividing by negative 1 over n squared, that is equivalent to multiplying. So I just take the reciprocal, so it's equivalent to multiplying by this. Now let's be careful. I've got a negative and a negative, so those are going to become two positives. And so when I multiply this together, so now I've got the limit as n approaches infinity of 8n squared over all this stuff in the bottom, and I'll go ahead and multiply it together. So I actually get 16n squared minus 1. Okay, so I still have infinity over infinity at this point. I could use L'Hopital's rule again, but it would actually just be easier if I just divide now the top and bottom by the highest power, which is n squared. So, okay, now let's make some space. And the limit that I'll get now is 8 over 16 minus 1 over n squared. And so then we can see, right, so this is going to go to 0 and the rest is just a constant. So this will be 8 over 16. So this equals 1/2. Now, we're not done. So remember at the beginning of this, right? So we took the natural log to get this whole thing started. So the whole thing with L'Hopital's rule when you're working with these indeterminate powers is then at the very end, you have to raise this on, really not to, on RE. So my final answer is going to be A-E-I-O-U, e to the 1/2. Okay, but what was the original question? So we just wanted to know, does this limit converge? So yes, it converges because I got an answer. So if that was the only question, does it converge? Yes, it does converge. Okay. And so that brings us to the end of this one. This was kind of a longer one. I do have other video examples if you want to see a few more. This is kind of a dense lesson, so this is a good one for extra video examples. If you found this helpful, I'd love it if you hit that like button. And otherwise, I'll catch you guys in another video. Bye!